Assalamu alaikum. I am Mohammad Jahangir Alam, lecturer in physics. I welcome you all in my online class. First of all, thanks to Almighty that I am still okay and carrying on my regular studies. He has given me the ability to take this class. Dear student, here I also hope all of you are well. By the mercy of Almighty and carrying on your regular studies, staying at home. Dear student, in our today's class, we are going to discuss a very important and realistic topic which are very closely involved in our practical life. You know, in our previous chapter from physics second paper, that is the chapter of magnetic effect of electric current, where we have learned from the Faradays Law and other discussion that how a moving charge can create a magnetic field. That is, in that chapter we have discussed about a moving charge or electric current can a magnetic field. But in this chapter we are going to discuss the reverse process. Right, you got it? That is, we are going to discuss how a variable magnetic field or moving magnet can create electromotive force or electric current. And this application of magnet or variable magnetic field is a blessing in our daily life. Dear student, so our today's class is very important and I hope you will enjoy it. Right? So we are going to start our today's class, and our today's class is we will discuss from the physics second paper chapter 5. That is our today's topic. Our today's chapter is electromagnetic induction and alternating current, right? Dear student, already you have got the idea what the electromagnetic induction is. So for our better idea or realization, we can see the definition of electromagnetic induction. In the definition of electromagnetic induction, they said that the process of creating electromotive force and current in a closed coil of wire due to the influence of moving magnet or current carrying coil is called electromagnetic induction. Right? Dear student, I hope you got it. Now we can see a video to realize it, which will help us to realize what the electromagnetic induction is. Okay?
Let us study electromagnetic induction by changing the magnetic field around a conductor. We have taken a bar magnet, a coil, and a galvanometer. The galvanometer is connected to the coil and is used to detect the current flowing in the conductor. Move the magnet into the coil and carefully observe the galvanometer deflection. As the magnet is moved near the coil, there is a momentary deflection in the galvanometer. As the magnet comes to rest, the deflection of the galvanometer stops. The deflection of the galvanometer indicates that there is some current flowing through the coil. The galvanometer deflects only when the magnet is in motion near the coil. Motion of the magnet is responsible for the changing magnetic field. This changing magnetic field is inducing the current in the conductor. This phenomenon is called electromagnetic induction.
Dear student, scientist Faraday shows by his two experiments the phenomena of electromagnetic induction or alternating current. In the first experiment, he used a bar magnet and a closed coil connected with a galvanometer. Right? He shows that when the bar magnet moves towards the coil and moves away from the coil, that is, when there is a relative motion between the closed coil and the bar magnet, there is a deflection in the galvanometer. Right? When the magnet moves towards the coil, the number of magnetic line emitted from the bar magnet enter into the coil, and when the magnet is moved away from the closed coil, then the number of line decreases in the closed coil. So in this phenomena he explained that when there is a variable magnetic field, magnetic field or relative motion between a bar magnet and a closed coil, there is a electric current or electromotive force produced in the coil. The directions of the deflection of the galvanometer will be opposite when the magnet moves towards the coil and moves away from the coil. That is, the opposite electromagnetic force or direction of current will be opposite when the magnet moves towards the coil and when it moves away from the coil, right? I hope you realize it. And in the second experiment he used two coil. First one is primary coil and second one is secondary coil. In primary coil he used a source of electricity or a battery, a variable resistance, that is by which we can create a variable current and which will produce a variable magnetic field. In our previous chapter we have learned that this type of coil act like a bar magnet. So regulating this variable resistance, we can create a variable magnetic field using this coil. And this is a secondary coil like this. When the current in the primary coil changes, that is the variable magnetic field is produced here, which will affect the secondary coil, or due to the change in the variable magnetic field in the primary coil, a electromotive force or current will induced in the secondary coil, right? And that's for that reason there is a deflection in the galvanometer. So if, from these two experiments we can realize that a variable magnetic field can create a electric current or electromotive force, or if there is a relative motion between a magnetic field or and a closed coil, a electromotive force or electric current is produced in the coil, right? The current which is produced in the secondary coil is called induced current, or electromotive force produced in the secondary coil is called induced EMF or electromotive force, right? Dear student, now we can see a video for our better realization.
We're going to have a look at Faraday's law of induction. For this demonstration, we've got a ring which consists of many turns of copper wire. Regrettably, it's covered with tape so they're not visible. It was known that when electricity went around a conductor, it produced magnetism. People had made electromagnets before Michael Faraday came along. If the magnet sits stationary inside the coil of wire, no electricity is made, and we can see that the meter needle is not moving. If the magnet is moved, the magnetic field within the coil of wire changes. And it is this changing magnetism that induces electricity. This is what Michael Faraday discovered. And notice that by moving the magnet in different directions, we produce electricity in either the forward or the backward direction. We can illustrate this with a bar magnet. The magnetic field of a bar magnet points away from the North Pole. And so we could imagine a series of magnetic lines coming from the north end with arrowheads pointing away from the North Pole and toward the South Pole. If I move that magnet into this conducting coil, I am increasing the number of magnetic lines that point in the direction I'm moving. So this is the reason that when I move a magnet in and out of an electric coil, I see my meter change directions and show me electricity moving first in one direction and then in the other. Another way to look at Faraday's law would be to produce electricity by induction and then use it. And so we've got an apparatus in which we have two coils, each of them placed vertically on the table, and above each coil is a magnet hanging from a spring. The magnets and springs are identical. If I move one of those magnets in and out of the coil, it will induce electricity. Second, we'll take a small battery and connect it to the second coil and see that when we put electricity into the coil, it produces a magnetic effect on the hanging magnet. and the hanging magnet moves vertically. So now we'll connect the two coils with wires and start bouncing the first magnet so it moves up and down at its natural frequency, producing electricity at that frequency. So the motion of the first magnet will be translated to the second magnet electrically, and we'll see the second magnet begin to move at the same rate as the first magnet because we are inducing electricity in the coil. The magnet doesn't just sit there, the magnet has to move.
Dear student, after the observation or observing the result of his experiment, famous scientist Faraday gave two laws of electromagnetic induction. To show honor to our famous scientist, these two laws are known as Faraday's law of electromagnetic induction, right? He gave two laws according to first law. In the first law, he said that whenever there is a change of number of magnetic lines of induction or magnetic flux in a closed loop, then an electromotive force is induced in that loop, right? This explains that or said that if there is a relative motion between a bar magnet and a closed coil, then a electromotive force is induced in the closed coil. If there is no relative motion, no electromotive force or no electric current. This is the basic of this law, right? Again, according to the second law, he said that the value of the induced electromotive force in the coil is directly proportional to the rate of change of magnetic flux in that coil. You know, a electromotive force is induced in the coil due to the variable magnetic field. The induced EMF or electromotive force will be directly proportional to the rate of change of magnetic flux in that coil, right? So, if the induced EMF is E, if the induced EMF is E and the rate of change of magnetic flux in a coil of single loop or single turn is d phi in time dt, then we can write that E is directly proportional to d phi by dt, right? So, we can replace the sign of proportional using a constant. So, we can write that E is equal to k d phi by dt, right? If electromotive force E time t and magnetic flux phi are expressed in SI unit, then the value of k will be 1. So, finally, we can write that E is equal to d phi by dt, right? This is expression for a coil of single turn. But if the number of turns in the coil is n, then the expression will become E is equal to n d phi by dt, right? So, this is the expression for the second law gave by Faraday. Dear student, now we will see and another important law which is known as Lenzs law. Scientist Lenz give the law, and the statement of the law is the direction of induced current is such as to oppose the very cause which is responsible inducing current or EMF in the coil, right? Dear student, to realize it, we can consider, suppose there is a closed loop and here is a bar magnet. Suppose this is north pole and this is south pole. So, from the north pole, a huge number of magnetic line of force will be emitted, right? When the magnet is moved towards the loop, so direction of the induced current in the coil will be anti-clockwise, right? So, anti-clockwise current in the loop will create a same type of pole, that is a north pole will be created due to the current in the loop, and which will oppose the north pole of the bar magnet. Again, when the bar magnet move away from the loop, then the direction of the current will be opposite. That is, when the bar magnet is moved away from the loop, then the direction of the current will be reverse. So it will be clockwise, and it will create a south pole in the loop, which will attract the north pole of the bar magnet. That is, which is stated in the statement or law by Lenz. They said that the induced current, the direction of induced current is such that to oppose the very cause which is responsible for the inducing current or EMF in the coil. Right, dear student, I hope you got it. Here we can see a video for our better realization of Lenzs law. Right, dear student, here is the important topic, Lenzs law and conservation of energy. Apparently, it seems to us that energy conservation of energy is violated here. By the experiment, we observed that when a bar magnet, suppose north pole, south pole, is when the bar magnet is moved towards the coil or move away from the coil, there is a electric current and current is induced in the coil. But you know, to produce a current, we need a electric source or a consumption of energy. But there is no electric source or no energy is consumed here. How the electric current is produced in the coil? So you can ask that how the without any consumption of energy, electric current or electromotive force can be created. Dear student, if you think very acutely, you will observe that when the magnet is moved towards the coil and move away from the coil, we have to use a mechanical energy. Here, due to the motion of the bar magnet, we have to use a mechanical energy, and this mechanical energy can create the variable magnetic field which will create the electric current. So conservation of energy is not violated here. So we can say that Lenzs law obeys the conservation of energy. Right? Now we will see self-induction. First we can observe the figure. Here is a closed coil which is connected with a source of battery and a key. If the current passes through the coil, if there is a steady current, that is, if the value of the current is constant, then no magnetic induction will be induced in the coil. But if the current varies, then it will also create a variable magnetic field. That is, induction will be observed in the coil. So they said that the electromagnetic induction which is produced in a single closed coil due to the change of magnetic flux which results for the non-uniform current. So, non-uniform current will require for the electromagnetic induction in this coil is called self-induction, right. Dear student, if the direction of current in the coil is like this, when we will increase the value of current, then the induced EMF, induced in the coil will be opposite to the current. That is, the property of the induced EMF will oppose the current, right. But when we will decrease the current, when the value of the current will be decreased, then the direction of the induced EMF or produced EMF will be same like the electric current. Then the electric current will assist the flow of electric current. So, from this phenomena we can explain that induced EMF in this coil E is directly proportional to the negative value of di by dt, that is the negative value of the rate of change of electric current, right. Dear student, from the expression we can write E is equal to minus L di by dt. Here L is a constant of proportionality. By replacing the constant proportional sign, we can introduce it. This L is called the constant of self-induction, constant of self-induction or self-inductance, right. Now, we will see the definition of L or coefficient of self-induction, coefficient of self-induction or self-inductance. We have already learned that the induced EMF E is equal to minus L di by dt. Here L is a constant of proportionality which is known as coefficient of self-induction or self-inductance. Dear student, in this expression, if we use the value of di by dt, if di dt is equal to 1, that is, if the rate of current, if the rate of change of current is 1, that is di by dt is 1, then we can write that E is equal to minus L, or numerically E is equal to L, right. So, from this expression we can give the definition of self-inductance or coefficient of self-induction. Okay. In the definition of coefficient of self-induction, they stated that if the current in a coil changes by 1 per second, that is the current di dt will be 1, that is the change of current by 1 in per 1 second, then the electromotive force induced in that coil is called the coefficient of self-induction or self-inductance. The unit of coefficient of induction is Henry, right. It is very important for your MCQ, right. The definition of 1 Henry can be given as, if due to the change of 1 ampere current in 1 second in a coil, 1 volt EMF is induced in that coil, then the self-induction of the coil is 1 Henry. It is a very important definition, right. Now, we will see the mutual induction. Okay. So, the statement is that electromagnetic induction which is produced in the secondary coil due to the non-uniform flow of current in the primary coil is called mutual induction. In the figure, if this indicates the primary coil, in the primary coil there is a source of electric current, a key, that is by which we can change the flow of current in the coil or control of flow of current in the coil. If there is a non-uniform current in the primary coil, due to the result of this phenomena, a electromagnetic induction will be induced in the secondary coil, right. And the induced EMF in the secondary coil also will affect the flow of current in the primary coil. So, this phenomena is called mutual induction, because this is occurring mutually between two coils, right. Dear student, if the change of current in the primary coil is denoted by di and which takes the time dt, then the rate of change of current in the primary coil is di by dt, and if the induced EMF in the secondary coil is E, then we can write that E is directly proportional to minus di by dt, right? So similarly we can replace the proportional sign by a constant, so we can write E is equal to minus m di dt. Here m is called the coefficient of mutual induction or mutual inductance, right? Dear student, I hope you got it. You have to practice this type of topic from your textbook, staying at home, but if you have any confusion you can call us. So thank you very much being with me in my class. May Allah bless all of you. Assalamu alaikum.